Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to two-dimensional motion, that is motion of an object in a plane. So previously we discussed the motion of an object in a plane with uniform acceleration with respect to the velocity vectors representation. In this video we are going to discuss the motion of an object in a plane with respect to the representation of the position vectors according to the individual components, respective x and y components. So again, basic definition of acceleration, which is change in velocity by time taken. So uniform acceleration is when a body undergoes equal changes in its velocity in equal intervals of time. So here we'll go back to the concept of displacement vector with respect to the position vectors, which we have discussed in the first video related to two-dimensional motion. So let us say we have an object which is, let's say, at an initial point here, at an initial point, let's say I, which is defined by its position vector RO vector with respect to the origin. From there it undergoes a displacement delta R vector to the final point F. The position vector of the final point is RT vector with respect to origin. This is the displacement or the change in position, that is displacement delta R vector. We know velocity vector will always be in the same direction, that is parallel to the displacement vector. So V vector is equal to change in position or displacement by time taken. Velocity is change in position or displacement by time taken. So it is delta R vector by T. Delta R vector is nothing but final minus initial position. Change in position is final position minus initial position. If you recall, we discussed it in the first video. RT vector minus R0 vector by T, or RT vector, the final position is the initial position plus change in velocity, or the change in displacement, change in displacement, not velocity, change in position, which leads to displacement here. Vt, which is equal to delta R T vector, which is the displacement of the object or the body. Okay, delta R T vector is equal to V vector into T from here. Okay, so final position of the object defined by this vector is equal to the initial position vector plus change in position, that is displacement, given by V vector into T. We know displacement is simply product of velocity and time. So same here, which is represented in terms of vectors. Now let's say we resolve it, each of these position vectors, initial and final position, in terms of their x and y components. So we have the initial position here, I, the initial position vector. Its x component is x0, RO vector, okay, R0 vector. So the x component is x0 and the y component is y0. So it is represented as x0 I cap plus y0 j cap. Similarly, the final position vector F, which is defined by this position vector RT vector, it has its x and y components as xt and yt. So it is represented as xt I cap plus yt j cap. These two things are clear. We have discussed it previously also. Next, we have the velocities, which we resolved in the previous video also, where u is the initial velocity of the object, v is the final velocity of the object. U has its respective x and y components, ux I cap, uy j cap. The final velocity v vector has its respective x and y components, vx I cap, vy j cap. So here change in velocity delta v vector is final velocity minus initial velocity. Okay, so we have written u vector is uxi cap plus uyj cap, v vector is vxi cap plus vyj cap. This is the final velocity, this is the initial velocity. So similarly we have the acceleration vector, its x component is ax, that is axi cap, and the y component is ay, which is represented as ayj cap. So a vector resolved into its individual x and y components, we can write it in vector form as axi cap plus ayj cap. Okay, so these two things are clear. Now next is, this is the first equation. Okay, acceleration is change in velocity by time taken, v minus u vector by t, or v vector is equal to u vector plus a vector into t. This is the first equation of motion, v is equal to u plus a t. Now there is the second equation of motion, which is represented as s is equal to ut plus half at square. Here s is the net displacement or the net change in position of the object. Okay, u is initial velocity, a is acceleration, and t is the time taken. So here from this representation, vector representation of the initial and final position, the net displacement which is equal to delta r vector. So this is vector, okay, it's not scalar, delta r vector, that is equal to rt vector minus r0 vector, final position minus initial position. Okay, so here net displacement is equal to rt vector minus r0 vector, final minus initial position. So the same thing we will write here. Okay, this s, we have substituted s as this. Okay, this is net displacement s vector, which is equal to change in position delta r vector, that is equal to ut plus half at square. Here we have vector notation on initial velocity and acceleration because it is two-dimensional motion. So u vector t plus 1 half a vector t square. Okay, this is s, this s, which is represented in vectors. Why? Because in one-dimensional motion, as there was no vector, the change in position was happening only along one direction. So the components, okay, resolving it into various components, that was not required. It was not necessary to include the vector notation. Okay, there was no requirement to resolve it into any component, into its individual components along x and y directions. But here, as it is required, so we have to include this vector notation so that we can resolve it into its individual components. So we can write rt vector, or the final position vector, is equal to ro vector, that is the initial position vector, plus u vector t plus 1 half a vector t square. This is the equation which we have. This is the main objective of this video, the representation of the final position vector into the x and y components. This. Now, if you see, we have r0 written as x0 I cap plus y0 j cap, rt is xt I cap plus yt j cap, u vector is equal to ux I cap plus uy j cap, v vector, final velocity, is vx I cap plus vy j cap. Now all we have to do is substitute each of these values, this vector, with their respective x and y components. Okay, resolving it into its x and y components. So we have this base equation, rt vector is equal to r vector plus u vector t plus 1 half a vector t square. So we write rt here as this xti cap plus ytj cap. We write rho as x0 I cap plus y0 j cap. We write initial velocity u vector as ux I cap plus uy j cap multiplied with t, okay, plus a, we write it as a vector, we write it as ax I cap plus ay j cap. 1 half a vector t square, so we have 1 half ax I cap plus ay j cap into t square, because time is not a vector, okay, this. Now what we have to do, like we did in the previous video, we have to bring all the coefficients of I cap, okay, on one side, okay, together. I cap, all the coefficients of I cap, that is x0 plus uxt plus 1 half axt square. This is 1. Then all the coefficients of j cap together. So we have y0 plus uy plus 1 half ayt square, coefficients of j cap. So we have separated the whole thing, the whole equation, in terms of the x component and the y component. So now we have to compare each side. So here xt, which has the coefficient of I cap on the LHS side, we compare it with this. So xt is equal to x0 plus uxt plus 1 half axt square. Similarly, yt, the coefficient of j cap on the LHS side, we compare it with the coefficient of j cap on the RHS side. So we have yt is equal to y0 plus uyt plus 1 half ayt square. So this is the thing. Okay, so if you see, in essence it is the same thing. That is, for the second equation of motion, S is equal to ut plus half at square, because here this xt minus x0, which is the net displacement or the net position, change in position across the x-axis, this is that xt minus x0, that is equal to uxt plus 1 half axt square. Okay, similarly here yt minus y0, that is the net change in position along the y-axis, this, that is equal to uyt plus 1 half ayt square, this. So this is the same equation, S is equal to ut plus half at square, but here this is applicable, the straightforward equation is applicable for one-dimensional motion, because there, as it is happening, all the things that are happening along a single axis, whether it is x, y, z, there is no need of resolution into individual components along x, y or z axis. So no need of that. But here again I repeat, as it is happening in a plane, so both components we have to include. So we have to write the respective component equations separately. So this is for the x side, same uxt plus 1 half axt square, the essence of the equation is same ut plus half at square. The format of the equation is same, just we are replacing the initial velocity and the acceleration with its respective x and y components. Ux, ax, here uy, ay. This is for x axis and this is for y axis. Okay, so here it is the same thing. So this is the final position vector representation for the motion of an object in a plane with uniform acceleration. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.